Let's see. Share. All right. Okay, well, I'm ready when you are. Okay, so we'll just hold off. Are we recording right now? Okay.
Please stand by while your recording connection is established. This conference is being recorded.
Alrighty. Well, I guess we can begin. It is 2 o'clock. Hey, everyone. My name is Scott Pearse. I'm a software developer over here at InCar, and I work on a package called Vapor, as you guys all probably know. And I'm here to show you guys a visualization walkthrough of a first-of-its-kind EF5 simulated tornado that was... It's a data set that was given to us by a scientist named Lee Orff from University of Wisconsin. And he has agreed to give us a small sample of his data to use for demonstration purposes. Before we begin, I just want to point out that Vapor is an open source and cross-platform application. So you can use it on Windows, Mac, and OS X. And you can download it for free at this URL down in the corner of the slide, www.vapor.ucar.edu. And if you guys have any trouble with installation, data conversion, or anything else, our team is available to answer any of your questions at vapor@ucar.edu. So a little bit of background about this simulation. The simulation is modeled after the May 24th, 2011 tornado outbreak that hit near Oklahoma City. It kind of hit everywhere near Oklahoma City, as you can see in this radar mosaic. It spawned 1 EF5, 2 EF4, and 2 EF3 tornadoes, resulting in 11 deaths and 293 injuries. The EF5 tornado traveled 63 miles. And so using soundings from this whole event, Lee, I guess, started with a parameterization to simulate this 30-meter resolution model, which is based on the CM1 model, which is similar to WRF. It just deals with the vertical layering a little bit differently. It has a higher vertical resolution than WRF typically does. It's a microscale model as opposed to a meso or synoptic scale model. It was run on Blue Waters, and the data output was it has 1.8 gigabytes per variable per time step. And the data set we'll be looking at has 12 three-dimensional variables. And so I believe Lee's total data set was around 3 terabytes in total volume. The data we have to look at is compressed a little bit. So it's not a completely perfect reconstruction of what Lee looked at in his videos and his analysis. But he is planning on making that data public once he has his initial research complete. And so the techniques that we'll be covering here will be applicable to the fully true data that he will release at some point in the future. Before we jump into Vapor, I want to give you guys a little bit of pretext into the kind of visualizations we'll be making. The first I should back up and say that Vapor is a toolset that is comprised of a series of renderers, each renderer doing a different depiction of your data. And the first renderer we'll be looking at is called the volume renderer, or DVR. It stands for the direct volume renderer. And basically what it does is it applies two things to a 3D volume. It applies color and opacity to your entire 3D volume of data. And we'll go over how those two things, color and opacity, can be specified to illuminate some of the features that you guys may have in your simulations. After the volume renderer, we'll talk about some kind of two-dimensional slicing renderers that we have that can take a cross-section of your 3D data and kind of depict opacity and color in the same way that the DVR does, but just through a two-dimensional slice. There's a couple of renderers that will do that, and we'll talk about those too. After that, we'll go into our Streamline integrator, which allows users to pretty much litter their study area with seed points that will integrate flow from those seed points, whether it's steady state in time or unsteady flow, which is time variant. We'll cover steady flow, which is time invariant, and if we have time at the end, I might be able to get into some unsteady flow too, which is a lot of what Lee renders in his visualizations. And by the way, if you guys haven't seen Lee Orff's visualizations, you should Google Orff Tornado. That will bring up a whole series of YouTube videos that he uses Visit as well as Vapor. And for all of his flow integration in the visualization, he uses Vapor. And so that will give you an idea of what is possible to do. And it goes a little bit outside the scope of this webinar, but it'll give you an idea of what you can possibly do. So anyways, after streamlines, we're going to cover isosurfaces, before isosurfaces, we'll be covering two-dimensional or three-dimensional wind barbs, which basically show wind direction on the grid. And then after barbs, we'll cover isosurfaces, which are kind of analogous to a two-dimensional contour, whereas where a two-dimensional contour shows the value of a variable along a line, an isosurface shows a value of a variable along a three-dimensional surface within the entire 3D region. We'll also cover how to apply color to your isosurfaces according to a different variable. And this might be useful, for example, if you're interested in maybe the dew point. You'll be able to make an isosurface of temperature and color it according to humidity, which can highlight different areas in your model that might strike a dew point or some area around that value. The last thing we'll cover is Vapor's data conversion process. And I should talk about how one of Vapor's most important features is its data format. Vapor's VDC, it stands for the Vapor Data Collection. The VDC allows users to progressively access different compression levels of their data so that they don't always have to be looking at the full volume and the full perfect reconstruction of their data, which is important because with these larger data sets, the volume of data can be so large that rendering can introduce latency that makes the exploration of the data kind of difficult. If you move your scene and you have to wait 5 minutes for it to re-image itself, it can really hold the user back. So with the VDC, you can scale back your compression attributes, and the rendering will occur much faster if you're looking at it at a lower resolution. This enables a better ability to explore your data, and then once you know exactly what you want to look at, how you want to color it, and how you want to render it, then you can crank up the resolution and let your computer run for maybe a day and render out this thing at full perfect reconstruction. So all that being said, I'm going to exit out of my PowerPoint, and the first thing I'll do is spin up Vapor. So I have it installed already. On Windows and Mac, you'll be able to click on this little V here at the bottom to open Vapor, but on Linux, you need to open it through the command line, through a command called Vapor GUI. Once it's installed, you just type Vapor GUI. It'll do the same thing as clicking on this button. And here we have the user interface. On the left is a listing of all of our renderers. I mentioned earlier that Vapor is comprised of a series of renderer tools that depict your data in different ways, and there's a tab for each renderer that we have. DVR being the one all the way on the right, the flow renderer. Amit. Amit is asking where the data is located. And the data is on our Vapor website under example data. And Amit's also asking if you guys should be running through the tutorial with us. I would recommend not trying to re-implement exactly what I'm doing. I would encourage you guys to just watch my use of Vapor. This will be recorded, so you guys can come back and re-implement basically what I've done. I think it might be too much to try to follow along step by step what I'm doing. So back to what I was saying. I guess we're getting a question about linking, and let me see. Yeah, link to the data. Okay, www.vapor.ucar.edu, and you guys will have to register in order to get the data. But it's under downloads, and you'll see this example data link, and then it will ask you to log in. And we have users log in so we can follow metrics on Vapor's use. My username is Pearse@ucar.edu, and then once you log in, there is this example data page. And here at the bottom, this data set right here, Lee Orff F5 tornado simulation, there's a tar.gz file and then a zip file. And either one of those will contain about 8 gigabytes of Lee's tornado data. Yeah, and I should also mention, I'm going to hold off on answering any questions until later. I think my demonstration will run until roughly 3, and then I'll have about 30 minutes of Q&A to answer any questions you guys have after that. So back to Vapor. I think I was talking about how the renderers are listed up here at the top, DVR being the rightmost one, followed by flow, isosurfaces, probe, etc. And each one of these renderers contains its list of settings here on the left. And on the right, we have what we call our visualizer. We can see up here visualizer number 0. This is where our renderings will take place once we've loaded data. So the first thing I'm going to do is go up to my data menu and click on Load Data Set into Current Session. Now I'm going to mention, I'm going to load let me load my VDF file first, because you don't have to load a Vapor data set necessarily. My data set is called orf4.vdf, and this has been converted into Vapor's VDC. So after I've done my load data set, I just wanted to point out that you can also directly import other data formats, and I'll talk about this more later. But if you import a data set, you won't be able to progressively access your data. You'll only have the pure reconstruction of it, but it's a quick and easy way to get data into Vapor. It just omits the ability to use the compression aspect of the VDC. So I've loaded Lee Orff's data set into Vapor, and here we have a rendering of our domain. I can navigate Vapor by left-clicking my mouse, and that will rotate the scene. Right-clicking will zoom out and in by right-clicking and dragging the mouse up and down. And then you can middle-click your mouse button, and that will traverse the scene. Right off the bat, I'm going to go to my DVR tab, and if you guys see up here on the top left, there's this instance 1 indicator, and you can have multiple instances of your renderer. So if you want different flow renderers, you can have 10 of those and render them all at the same time. For my DVR, I'm going to click on instance 1, and right now we can see our first rendering of our volume of Lee Orff's data. But you can see it does look like it is compressed, and it is. And the way we control that is over here. It's kind of the first option in our menu list. And an easy way to control the compression level that we're looking at is through this fidelity controller. Vapor will give us a default set of little radio buttons that we can click on. And the lowest fidelity that we can look at is on the left, and I'll click on that. And there's not too much change to what we were seeing. Sometimes it's hard to notice the change between compression levels. But you'll notice, I'm not sure if you guys can see this, but my renderings are happening pretty quick. Once I crank up the fidelity to our true reconstruction of the data, you can see the image quality is increased once I let go of the mouse. And it does take a couple of seconds for Vapor to recalculate that rendering. And so depending on the size of your data set and how much you're looking at and what you're rendering, this fidelity controller can be very helpful in speeding up the time it takes to get a rendering completed. One thing I do want to note, I'm going to go up here to my Apple icon and click About This Mac, and I want to show you guys the hardware that I'm using in this application. This is not exactly slow hardware, but it's not a supercomputer either. It's a 3.1 gigahertz Intel Core i7 using an Intel graphics processor, Intel 6100, which is capable, but it's not like a dedicated NVIDIA GPU or anything. So that's kind of why the Vapor data format shines through so well, is because not all computers are capable of rendering these large amounts of data. And so what you can do on commercial hardware is just crank the fidelity down and explore your data that way. So I guess back to our rendering. This is our first rendering of our volume renderer. And you can see color is being applied to different values of the variable. But the question is, how is that being done? And so in my settings tab, I'm going to scroll down a little bit and kind of highlight this area right here. This area that I'm circling with my mouse is called the transfer function. And this is what controls how that color and opacity are going to be applied to our volume. The basis of the transfer function lies in this histogram that we see right here. This histogram is a mass distribution of our variable. It's just how frequently the different values show up in the volume. And we can see by the data bounds down here that our variable we're looking at, which happens to be buoyancy, written in red right there, our buoyancy ranges between negative 3.5 to 0.8. And so this is that range of values just pretty much stacked up in how frequently the values occur. So if I go to the peak right here, I can see that buoyancy, this is about at 0. It says about a buoyancy value of 0.003 is about the peak of the witch hat. And if we look directly below that, we can see this color bar has a green coloration to it below that value. And that basically corresponds with the green that we see in the cube. So it basically means that the most frequently occurring color that we'll see in this rendering is green. The very low values over here on the tail around negative 0.35 are going to be drawn in red. And the very high values of buoyancy will be drawn in purple. And all the colors, or all the values in between, will be represented by the colors in this reversed rainbow. So that's, I hope I'm being clear on how color is being applied. It's basically whatever color falls underneath the value in this variable histogram is what will be drawn at in the renderer. So that's how color is drawn. Opacity, on the other hand, corresponds to this green ramp right here, which I can control by clicking on. There's these 4 gray squares. I can click on those and drag them up and down. And basically, the higher up this curve that is overlaid on the histogram is, the higher up it is, the more opaque the variable will be drawn. So if I drag this all the way up, we have maximum opacity and all values in the data are being drawn completely opaque. There's no transparency. If I drag them all down, like this, you can see some of the values are starting to disappear, and once they're all down, there is no data being drawn whatsoever. And so by controlling these points, I can adjust which values in the data are being highlighted more than the others. So by doing what I've done here, by adding a little ramp at the end of this witch hat curve, at both ends, at the high end and the low end, we're now showing buoyancy data of the tornado, of the values that fall within the blue, pink, and pink colors at the high end, and the red and yellow colors at the low end. Let's see. Another thing I should probably segue into right now is our variable selection. So right now we're looking at buoyancy. And we can pick other variables through this drop-down menu right here where it says variable. And these are the variables that are contained in the example data set. And like most models, the outputs are usually like a U, V, and W, wind vector. We have vorticity values, and a few other things like simulated reflectivity. One of the coolest features of Vapor, in my opinion, is the ability to recalculate a new variable from pre-existing variables. So I'm going to show you guys how to do that right now. I'm going to calculate wind speed based off of our U, V, and W default variables that are in the model. So to calculate wind speed, I'm going to click on the Edit icon, click on Edit Python Program Defining a New Variable. And I didn't mention I'm doing this through a Python interpreter. When I click on that Edit button, I have this editor come up, and it's going to have fields for my input variables. They can be input 2D, they can be input 3D variables, and for wind speed, I'm going to pick as my input variables U interp, V interp, and W interp. These are interpolated values for U, V, and W. And then for my output variables, you can also select output 2D or output 3D. I'm going to add a 3D variable called wind. Click OK. And then down here we have our Python interpreter window. I'm going to type wind equals sqrt u interp times u interp. And this is just 3D magnitude plus v interp times v interp plus w interp times w interp. And then we can test the script. And on a successful test, we can click OK and then apply it. So this new wind speed variable will show up in our variable list, and I'll scroll down and pick that. And you'll notice that it's taking a little bit longer to render wind speed than it did for buoyancy. That's because we're loading 3 different variables, U, V, and W. So it'll take about 3 times as long to issue renderings of this derived variable in particular. And this doesn't quite look like wind speed. So I should point out that Vapor doesn't always result in a good default transfer function. And so there's 3 magic buttons that you pretty much should memorize if you're using the transfer function and making edits like that. These 3 magic buttons that will correct your transfer function are called fit data. So I'm going to hit fit data. And then I'm going to hit fit to view. And then histo. And basically what that did is that I changed the data bounds, which are shown here as for wind speed about 0.6 to 125. And fit data applies those bounds to the transfer function domain bounds, which are here and here. Those are kind of like the left and right edges of the transfer function. Fit to view changes the transfer function window to look at the transfer function domain bounds, and then histo recalculates the histogram that we see. And so this is our wind speed. If you guys notice, the transfer function we're using right now is the reversed rainbow, which is what I believe WRF users typically expect as a default color map. Vapor also has other transfer functions that come along with it. And I'm going to change it to my favorite one. So to go to my favorite transfer function, we click on Load Installed TF. And this one at the top is my favorite. It's abbreviated. It stands for black, blue, aqua, green, yellow, orange, red, violet, white, .vtf. And I don't know, I like this one a lot, personally. I typically use this in my visualizations. And the last thing I'll show you guys with the transfer function is how to easily edit the transfer function range with these red arrows at the top. I'm going to take this red arrow, which is going to change the region of data that I'm looking at. I'm going to move it over until I hit a value of about 45. And that's going to squeeze my rainbow in so that instead of looking at the data bounds of 0.6 to 124, now I'm looking at 45 to 124. I'm going to do the same thing on the other side and bring that down to 85. So I'm going to squeeze this rainbow down to 85. And now my color is being applied to only, well, I guess my rainbow is being applied to the colors between this range. And on either side, I have black and white being applied to all colors outside. I'm going to now apply some opacity so we're not seeing so much of the black in the region. And I'm going to remove some of my opacity control points by right-clicking on those gray squares. I'm going to right-click on it and then hit Delete Control Point, Delete Control Point, and Delete Control Point. And then I'm going to apply a simple ramp to the data, which increases in opacity as we get higher in the variable value range. And so now we have basically a 3D rendering of wind speed of our F5 tornado. Let's see if we can get a better perspective on this. So you guys can see the color variation a lot through the top, which is the edge of our domain. But around the sides, it's really hard to see through. I mean, it's basically pure blue on the side. And Vapor offers a way that we can kind of cut through the data and see into it. It's basically a way to control the region of the data set that we are going to draw into. And so if that doesn't make sense, maybe it will if I demonstrate. So to reduce the region that I'm drawing to, I'm going to go up here to the top left into this drop-down menu. We call it our mouse mode, and that's because it's a way for us to use our mouse to edit the region that we're drawing to. I'm going to click on Region, which controls the region of that our DVR is drawing to, and we see this red cube show up. And on this red cube, there are 6 of these little red boxes that control each side of this red cube. So I'm going to right-click on this red box. I'm going to drag it over, and I'm going to see if I can get the vortex. I think it's about right there. And this should give us a cross-section of the vortex along with a 3D rendering of everything that is inside this red cube. So that kind of gave us a way to peek into that volume rendering and see what's going on inside. Mouse modes apply to all of Vapor's renderers, and so I'll be using that a lot through this demonstration. Okay, so that was our volume renderer. The next thing I'm going to show you guys, I'm going to go back to my DVR, scroll up, and I'm going to do flow lines next. So I'm going to turn off my DVR. I'm going to stretch my rendering region back out because we want our flow lines to appear in the entire volume. We don't want those to be cut off in the same way our DVR was. So after I do that, I'm going to go to our flow renderer, which is the next one over to the DVR on the left. And basically, I guess I can just go ahead and turn it on just to get a rendering of something right now. But this is obviously incorrect. This is not using our wind vectors. So to apply those in our settings menu, there is this steady field menu with an X, Y, and Z component of wind vectors. I'm going to click on X and select U-interp. On my Y value, I'm going to do V-interp. And for my W, I'm going to do W-interp. Or my Z will be W-interp. And so we got something that does resemble wind speed, but it still doesn't make too much sense. So what I'm going to do next is go to my flow rake mouse mode. And this will allow me to select where I am placing my seed points, where my flow lines will begin. And right now it's randomly allocating seed points within my entire region. There's a home key I'm going to click, which will take me to my original view, the top down, looking down the Z-axis. And I'm going to reduce my, my flow rake to a very small sliver down towards the ground, like that. And so now we have a random allocation of seeds. that is within this red box towards the ground level of the tornado. But I personally don't like doing random allocations of seeds. I like to do mine in a grid. And so in order to change that setting, there's this drop-down menu called Show Flow Seeding Settings. I'll click on that, and we can see right here we are using the random rake. I'm going to click that and select the non-random rake, which will then let me specify the dimensionality of my seed placement. Right now I'm doing 1 by 1 by 1, and I'm going to do instead 50 seeds on the x-axis, 1 seed on the y-axis, and 5 seeds on the z-axis. And that should render. Maybe my region's a little bit off. I'm going to pull this out in towards the tornado. Okay, and there we have our seeds. A 50 by 5 allocation of seed points that are all being sucked into the tornado right now. Now there's a few other settings that can make for a better visualization further down. One of them is line smoothness, and if we look real close, we can see that there are a few jagged edges on these seeds, and so we can turn that up at the cost of computational power. This whole act is kind of a balancing act between how many seeds you have, the smoothness, the flow length, and the compression level you're looking at. And if I scroll back up, you can see I'm at a pretty low compression level. So that allows me to have a lot more seeds, smooth them out, and I can also increase their flow length. So I'm going to scroll back down, and I'm going to crank up my flow length. And finally, we can see some of those seeds actually being pushed into the tornado. For demonstration purposes, I don't know, it might be risky to do a stress test in the middle of a presentation, but I was doing this earlier, and I think it worked. I'm going to do 50 on the z-axis, and you can see, I don't know if you guys can see by the frame rate of my computer, but it's a lot slower than it was before because I'm rendering 50 more seeds than I was before. If I clicked on high fidelity right now, I think my computer would come to a crawl, and I'd probably have to come back in 5 minutes before the rendering was actually complete. So once again, it's kind of a balancing act between the fidelity that you're using, the dimensionality, how many seeds that you're planting. Right now I have 2,500, and the line smoothness and flow length. The last thing I'll show you guys with flow is that you can change the color of the flow. I mean, maybe you don't like red. Right now we're using a constant color, and under this color and opacity mapped entity, you can actually have the color according to position on the flow by the seed index, or color it according to a different variable. Like I'll try simulated reflectivity right now. And this is basically, like I said, simulated radar reflectivity. These color mapped entities, like DBZ, will have a transfer function just like we saw in the DVR. And the transfer function doesn't look clear, so I'm going to hit those 3 magic buttons: fit data, fit to view, and histo. And there's our simulated reflectivity curve. And then from there, you can change its opacity and color mapping according to how you see fit. So that's basically it for our flow renderer. Next, I'll move on to a simpler renderer. Before I move on, I should mention, again, this is steady flow, so it's time invariant. If we wanted to do a time-varying flow simulation where we're just dropping particles into the simulation like what Lee does throughout his visualizations, we would want to use unsteady flow, which has a few more parameters that are a bit more complex, but I can talk about those later, maybe at the end if we have time. Okay, so that's it for flow. I'm going to turn my flow renderer off. I'm going to go back to my navigation mouse mode so we don't see any more red box. And I'm going to click my home key, going back to the top-down view of our data set. The next renderer, I think on my list to cover, is called Barb's, and that's the one all the way on the left. Barb's is kind of like flow in that you need to specify a velocity field on X, Y, and Z. I'll just turn it on so we can kind of see what it's doing. And if I zoom way in, you guys can see these tiny little arrows that are getting rendered. but they're not using our wind field, our X, Y, and Z components of wind. So we have to specify those once again. So I'll select uinterp, vinterp, and winterp. And we can kind of get an idea of what the wind is doing at the mid-level in our data set. But I'm kind of interested in what's going on at the ground. So I'm going to go to our Barb Rake mouse mode, and I'm going to right-click on the top control point and then squeeze it all the way down so that the barbs, well, maybe that was too far, right there. So now my barbs are on the ground. I can click on the layout options and then specify what kind of grid I want my barbs to show up on. I'll do 100 by 100. And now we can kind of see what the wind field is doing a little bit better at the ground. I'm going to turn my Barb Rake mouse mode off. And then, like with Flow, we can click on the appearance options, and we can have another color map variable. So let's see, we could do wind speed, that derived variable that we had before. And this is I guess a rendering of arrows showing what direction the wind is going and the magnitude, I guess colored by velocity. So the long arrows are blue. I guess I don't know if we have any purple ones, maybe one or two. But once again, you guys can see in the transfer function, purple is our high color and red is our low color. So we have very little movement over here and very high movement in the funnel of the vortex. The probe can also be three-dimensional. So right now we have a dimension of 100 on the X and Y dimensions. But on the Z, we can crank that up to 2 maybe. I don't want to break my computer during a demonstration because the more of these I add, oh, I guess I added 12 right there. So that's not bringing my computer to its knees yet. So I guess I can go to my Barb Rake. I can drag this up, and this will just distribute those barbs in that grid that I specified, 100 by 100 by 12. And well, I hope that kind of gives you guys the idea of what's going on with the Barb renderer. I'm going to scroll up and turn that off. And I'm going to talk a little bit about our more two-dimensional renderers, starting with what we call the probe, which is essentially a slicer. I'm going to go over to my probe tab and enable that. And then I'm going to go to my mouse mode and click on the probe mouse mode. And you can see this like two-dimensional square in the middle of my data set. That's where my probe is going to be rendered, so I'll go ahead and enable that. And then I'm going to click on my probe layout options. If I scroll down a little bit, there's this button called Fit to Domain. I'm going to hit that, and that's going to stretch my square out to cover the entire domain. And I think the compression is a little low to get any valid information or useful information out of this. So I'm going to throw the compression rate up. And I think we're looking at buoyancy once again here. Yes, under my variable, I'm looking at buoyancy. I'm going to use my mouse mode to right-click on that square and drag it. Oh, I'm sorry, left-click on that square and drag it down. And here's a depiction of buoyancy. We can also control the location of the probe through these controls over here where it says probe and contour center. We can use these X, Y, and Z sliders to drag it up to different positions or even specify one that we have in mind. If I don't know if 0.5 is a valid one. Yeah, it's at the very top. We can also control the probe and contour size on the X and on the Y axes. And we can also rotate this thing about the axes themselves. So it doesn't have to be axis aligned. If that doesn't make sense, maybe I can show you. If I take this rotate about axis wheel and spin it, then my two-dimensional probe is now rotated about that axis. I can do it on X, Y, and Z. Just like our other renderers, we can scroll down to our transfer function and hit fit data, fit to view, histo, and here's our buoyancy variable within this probe square that we've specified. Our transfer function updates itself, and it changes itself every time we make adjustments to the region that's being rendered. So if I read, whoops, manipulator not axis aligned. Okay, I can ignore that. Why don't I create a new probe for this demonstration? And then I can scroll down just to show that I can change the shape and size of the area that's being rendered to, and that changes the buoyancy histogram that's inside of it. So this histogram is representative of the data that is within the red rendering square or cube, depending on whether you're looking at a 3D renderer or a two-dimensional renderer. So those are the basics of the probe. I can scroll up. I'm going to disable my probe, and I'm going to go 1, 2, 3 renderers over to our contour renderer, which is very similar to probe. Same basic principle. I'm going to go to my contour mouse mode, and let's see, hit my home icon. And the same idea applies. I'll go ahead and enable it, and I guess the default color on our contours is white, and so I guess I have a white background right now. I'm going to scroll to the bottom and uncheck Use Single Color. So when I uncheck Use Single Color, that means that I will now be using this transfer function up here at the top. And instead of that opacity ramp that we had before, now we have an ISO value selector, which we can drag along the histogram to pick the value of the contour that we're going to show. I'm going to hit Fit Data, Fit to View, Histo once again. I'm going to put this ISO line or contour, maybe somewhere right there. And I can increase the count, the number of contours, by editing the count editor up here. I'll change it to 10. And then we have 10 contours that we can individually move around in this ISO line histogram to, I guess, illustrate the values that we want to show. Like the probe renderer, we have the layout options, which let us center the red square on X, Y, and Z. And we have the planar size, which we can reduce the size with. And we can also rotate about all of our axes. So the same controllers exist for the contours as do for the probe. I think the last renderer I'll show is the Isosurface renderer. So first I'm going to undo my contours. I'm going to enable a probe just to give us a frame of reference of where we're looking at. So I've cranked up the fidelity on our probe. I'm going to go to our probe mouse mode, drag this to the bottom with my left mouse button. I have to get inside of the domain, and then I guess I'll just hit Fit to Domain. Oops. Drag this back down. And then for our Isosurface renderer, I'm just going to come over here, and some of the same principles apply to the Isosurface renderer as do to the contours. I can go ahead and enable it, and we have our first Isosurface of buoyancy. It's at a pretty low fidelity. So I'll tell you what. Lee Orff is particularly interested in this field called vorticity magnitude. So I'm going to make an isosurface of vorticity magnitude. And to do that, I need to edit another Python program defining a new variable. I'm going to go up here and click on, basically vorticity magnitude is the magnitude of vorticity, as you might guess. I'm going to click on xvort, yvort, zvort, and then my new variable will call vort mag. Vort mag equals sqrt xvort times xvort plus yvort times yvort plus zvort times zvort. I'll test that. Success. Apply. And I'm going to go to the second highest fidelity for this. Oh, I should have picked my vorticity variable before I hit that, but looks like we're okay. And then on my variable selector, instead of buoyancy, I'll scroll down to vortmag. And this should show us a whole bunch of strange, like worm-like structures that are the vortices that are swirling around and causing constructive and destructive interference to the tornado. Hopefully this doesn't take too long. There. Okay. Now I'm kind of nervous about this because it takes a long time to load all 3 variables and make an isosurface. So the isosurface is one of our most GPU demanding renderers, and so it takes, I think, the longest of all of them. I think for our vorticity magnitude, the ISO selector works the same way as with contour. So I'm going to click on this. I'm going to drag it over to this peak and see what happens. Ooh, man, I guess that's too much to even comprehend. But I hope, whoa, gosh. Maybe I'll try a different value. How about that? Go a little further. Okay, that's kind of a better picture of what Lee typically looks at. You can see these worm-like structures that are following along this. I believe this is a rear flanking downdraft here on the right, and these vortices form along it and just get sucked into the tornado, either growing or shrinking it. The last thing I'll show you guys with the renderers is if I scroll down, just like with the flow and the barbs, we can apply color to this surface according to a different variable. And it works just the same way as it does for the other renderers. We just click on this mapped variable drop down, and I'll go ahead and just color it by, how about our W wind component. And then our transfer function will then populate. Oh, it actually populated pretty well that time. And so now we can compare the magnitude of the vorticity at the value we picked, which is, let's see, our value is at 0.3. So a vorticity magnitude of 0.3 can now be compared to a wind velocity between negative 40 and roughly 80. So I think that settles it for all the different renderers. The last thing I'd like to show you guys is how to convert your data. And there's 2 ways to convert your data. Let me minimize this. And the way I would recommend is using this tool called the VDC Wizard, which is a wizard application that will step-by-step take you through the conversions of your data. I should say that creating VDC is a 2-step process. First, you have to make a VDF metadata file, which describes the structure of your grid, all the variables that are inside of it, and the compression parameters that are applied to the data. And then there's populating the VDC, which is where you actually apply the wavelet transform to the data. And that's what allows you to look at your data at different refinement levels. So for demonstrations, I will click on Create VDF, and I will browse to a directory. Let's see. We'll go to Users, Pearse, and then Data, I believe. And then should be an ORF directory. Or I'll just put it in my data directory. I will call my file test.vdf, save that, and I'll browse to my source files so that I'm going to use WRF files for this example, and I have 3 files right here that I will open. And then I have to select the data type. The VDC Wizard only works with the data types we see right here. If you have more generic NetCDF data, there are command line utilities, which are they have a little bit more of a complex incantation. If you guys have trouble with those, send us an email and we can help you with the command line conversion tools for NetCDF, or there's a few others. But for this one, I will click on the WRF data that I'm using. And then next we have a list of all the variables that were read from those files. And we'll go ahead and create that VDF file. And then when we populate the data, this will actually apply the wavelet transform. I'll click Finish. And here we have a progress bar indicating how close we are to the end. So instead of waiting for this to finish, I'm also going to show you guys actually in Vapor. I'm going to open a new session doing away with everything. I'm going to do a new session, and do away with everything I just did with the tornado data set, I'm going to show you guys the direct importation feature in Vapor. So if you have WRF files like this and you don't want to convert them, you can just click on Data, Import Data into Current Session, WRF ARW. Looks like the wizard actually just finished. I'm going to exit out of that though. So Data, Import Data into Current Session, WRF ARW, and then navigate to my data directory, and then I can select my WRF files and directly load them. And you'll notice my fidelity controller now only has one option. So I'm looking at this at true fidelity. There is no compression feature. And so if this takes me a long time to render, then I'm stuck with that unless I convert my data. Now with this meso and synoptic scale stuff, like what WRF is typically dealing with, the X and Y axes are significantly larger than the Z axis. So in this data set, I think this is a Hurricane Katrina data set, you typically want to stretch the Z axis. And to do that, I'll click on Edit, Edit Visualizer Features, and there's all sorts of different features we can add in right here. The first one I'm going to change is my scene stretch factors on X, Y, and Z. I'm going to stretch Z by a factor of 60, and I'm actually going to turn on some arrows that indicate what axis is which. So X, Y, Z will correspond to a red, a green, and a blue arrow. And I'll turn on a time annotation for how about a date and time stamp. If that's included in your data, that can be shown in Vapor as well. So I'll click on that and then click on Home. And now my Z-axis is stretched by a factor of 60. I have indicator arrows showing what axis is what. And I don't see my time indicator, so I'm guessing my files don't have time data in them. With this data set, there's another renderer I would like to show real quick. Lee's tornado data didn't have any georeferencing information in it. So this Hurricane Katrina data does. And if you'd like an image of like Big Blue Marble, for example, you can go to the image renderer, click on Select Installed Image, and then double-click on bigbluemarble.tms. And then if we enable that, we have an image of Blue Marble kind of stuck in the middle of our domain, which doesn't make too much sense. So what I can do is click on Apply to Terrain. That will push it down to the bottom. And it will even map a height variable to the surface. And so I know this is the North American Southeast, and so it's a pretty flat area, but I guess we have some mountains in Cuba, so maybe you guys can see there is terrain being applied to our Blue Marble image. It's a little hard to see, though. And so if you guys do want an image in your data, that's one thing that you can do. Let's see. You know what? I think that's about it. So I don't know. Should we go to questions now? Yeah. So guys, we have a chat screen open up in the room, and we've had problems with crosstalk when we open up the microphones, and so I think what we're going to do is hit up questions on the chat box, and I think I see one question by Giancarlo. Do those transfer functions come with Vapor? And so, yes, they do. I'm going to show you on my DVR panel. If I enable my DVR, right now I'm looking at elevation, but if I scroll down, I can click on Load Installed Transfer Function, and we have all these different transfer functions. My favorite is the one at the top, but there's a whole bunch. Blue, red. You can see, there's a whole bunch that come with Vapor. It's hard to visually see what the colors are that are in the transfer function, so it might take a little bit of experimentation, but just click on Load Installed Transfer Function, and there's all these different transfer functions that are at your disposal, and you can also save the transfer function. So let's say I take this transfer function and I make a few changes to it. I can save it, and I can call it my TF, save the transfer function. I can save it in the session, or I can save it as a individual file that can be used in other applications. And so I guess I didn't mention sessions either. I'm going to save this transfer function to my session. And basically what a session is Vapor's state. that relates to your data. So if you went through, say, the tornado data set and made all these different renderers, you can save that state by clicking on File, Save Session, and then you should get a file dialog. Maybe it's buried back here. But you should get a file dialog that will let you save your session and then reopen it at a later point in time and then re-enable your renderers as you see fit. So I hope that answered your question, Giancarlo. Does it georeference automatically from Amit? That depends on what your data set is. Typically, WRF data sets will come with a proj string that describes where the domain exists in space, and WRF data sets will automatically be georeferenced by Vapor. And there's a few other data sets that will do the same thing. If you're dealing with generic netcdf data, you'll have to write your own proj string, and there's directions on how to do that on our website. And if you have trouble with that, shoot us an email and we can help you with that too. Giancarlo has another question. Where can we find a link to this tutorial? So basically the link, once we're done recording, you can go to the Vapor website. And the tutorial, I'll post a link under our current news section. And I'll also have a link under our training tutorials section. And there's a few other video walkthroughs that you guys can watch there right now between now and the time that it takes to get the webinar, I guess, encoded and uploaded. And I think there's another webinar that was done a couple of years ago. So I'll have a link on the Vapor main page and in the tutorial section as soon as it's available. And then Amit is asking, how does it handle different coordinate systems like Mercator and others? That is all handled in the proj string. And so that's typically done in WRF files automatically for you. But if you don't have a proj string in your data, we can help you out with that. Or you can check out our documentation. Okay. That's all right. Samuel, is there a way to load in multiple data files, such as multiple WRF output times, to create an animation? I guess I didn't show you guys the... Yes, okay, so you can load multiple WRF data files if they're on the same grid. So when I directly imported my 3 WRF files, they were a time series of WRF, and I'm going to go ahead and I'll make a new volume renderer of, let's see, just to illustrate time series in Vapor. I'll select Q, Vapor, and let me see if I can knock this down. So I know this isn't the prettiest rendering right here, but in order to advance your data in time series, like for example, if you make a VDF file out of a time series of 10 time steps in your data, all you have to do is click on this play button, and Vapor will iterate through each time step. That might have been too fast. I'm going to single step backwards in time with this reverse button. So now we're on time step number 1, if you guys can see that at the top, and now we're at time step 0. So I'll go forward again to 1 and 2. And then if you guys want to make a movie out of Vapor, out of your renderings, what you can do is click on the capture button and click on begin image capture sequence in Visualizer 0. It'll ask you for a name of files that you want to write out, and I'll write just test. And test will be appended by a 4-digit number that represents the frame that it is captured, that Vapor is captured. So I'll click save, and looks like test is already taken. Just do T. Save, and Vapor is now capturing every snapshot. So every time I click the mouse and move the scene, Vapor is capturing a screenshot, and every time I advance or go back in time, Vapor is capturing a screenshot. I can press the play button, and again, Vapor will capture a screenshot for every time step that goes by. And gosh, I'm not sure where I just saved those files to, but if they're not in my root directory, here they are. So I guess I ended up capturing 20 some odd screen captures with that whole sequence. And from those images, you can make a movie using a tool like Xsede is one that we highly recommend. And in our next Vapor release, we plan on integrating a cloud-based service called Xsede, which will actually generate a movie for you, upload it to their website, and allow you to share it with others. But you can also use tools like ImageMagick or FFmpeg to convert files on your own local computer. You just have to install those applications. Again, they're called Convert or FFmpeg. I hope that answered your question, Samuel. Can you create videos of changes through time with Vapor? Patrick, I hope that I was clear on that. Okay. So if I wasn't clear, ask again, and we can get to that. Amit asks, could you go over the process of converting netCDF data again? So netCDF is kind of esoteric incantations. I'm going to ask you guys if you would like us to convert your netCDF data or help you with that conversion, contact us directly. I don't think I have time to go through it quite right now. But basically, once you've installed Vapor, command line tools will be available to you. And to convert your netCDF data, the two commands, like I said, creating VDC is a two-step process. You need a metadata file, and then you need the wavelet translated wavelet files. That two-step process is done with netCDF with ncdf vdf create. And when I do that, we'll get a little help menu that explains all the different options that you can use. And there's a lot for netCDF because it's kind of like abstract. I will say that one thing that will help you convert netCDF data is that if you make it CF compliant, it will be tremendously easier to get it into Vapor. So that first command was ncdf vdf create to make your VDF file. And then to apply the wavelet transform, the command is ncdf 2 VDF. And then there is a smaller list of help options for that. Okay, got a question from Arash. Is it possible to load part of the data instead of the whole data set for a large data set in the order of terabytes? It is possible to convert a subset of that data set by picking your variables and time steps. If I scroll up here, you can see that there is I don't know if you guys, I'll blow this up a little bit. There is a start time parameter that you can specify. There are variable names that you can specify, so you can reduce your data in that way. But for direct importation, if you have a multiple terabyte file, it's going to be sucked in its entirety. If that's giving you tremendous problems, I would recommend either CDO or NCO. There's applications like NC Kitchen Sink that will let you extract time variables and hyperslabs from your data, and that could probably help you to reduce the size. Got a question from Matt. Can you access variables at a particular time step within the Python derived variable editor? Example, WRF precipitation is an accumulated variable from start of the simulation. I didn't know that. Say I wanted to create, for instance, a preset variable that is just the amount from each time step. So what I like to do is rain hourly t equals rain t minus t minus 1. Can that be done? Time is not an independent variable as far as I'm aware in our interpreter. So I think that would be a painful process of creating many precipitation variables that each were a subtraction of precipitation at another certain time. I think it could be done. It might be tedious. Okay, another question from Amit. Any plans to include that netCDF conversion in the GUI itself. That's something I'd really like to do. I'd like to do that, as well as we have a converter for raw data. So if you have raw binary data, I'd like to implement that into our GUI. But we currently do not. We have a long list of requirements that we're working on, and we haven't heard enough of an outcry from the users to actually implement those things yet. There's other things that are taking priority right now. But if the users really want something like that, we have a feature request forum, and we're on that all the time, trying to look for the next best requirements that we have to implement in Vapor. Question from Mark Richardson. Under import data into current session, you have the Ramses format, which is simulation code I use. Right, Ramses is a, astrophysical modeling software. However, it's not listed on my version of Vapor. Is that available with a more recent version of Vapor? Yes. So Ramses was introduced in Vapor version 2.5, which came out, I think, last November. Oh, no, I think it was January, actually. So that's brand spanking new. If you want to use Ramses, get version 2.5 off the website, and you can play with it there. Question from Theo. How can stereo animations be generated? Okay, two prerequisites for stereo generation. Number one, you need a graphics card that supports quad buffered stereo support. So if you don't know whether you have that, you'll probably have to look up your graphics card model number and look at its feature list. It needs quad buffered stereo support. Second requirement is that your screen needs to have quad buffered stereo rendering support, which means it has a higher, about double the refresh rate of a standard screen. So I think it can get up to about 120 hertz. If you have those two hardware requirements, you can enable stereo rendering by going up to your Vapor menu and clicking Edit User Preferences, and then there is this checkbox down here. It's disabled by default because vast majority of people don't have this hardware set up, but you can click on Enable Stereo Settings at Startup, and then Vapor will warn you it's not going to take effect right now. You've got to restart because we have to reinitialize all the rendering buffers. So we'll click OK, and then once you do that and you restart Vapor, you will be able to do stereo rendering by going to your View tab, and there are these stereo controls that are disabled by default. If you have the right hardware and you click that Enable button, these two guys will be enabled, and you will be able to create stereo sequences and movies from your data. Next question. How do we add a color legend? Yeah, good question. That is done, again, under the user preferences. Oh, no, I'm sorry, that's visualizer features. So to do that, let's see, I have a DVR right now. If I wanted to add a color bar for my DVR, I would go to Edit Visualizer Features, and then if I scroll down under Visualizer Features, there's Display Color Scales for current renderers, and we can pick what renderer we want a color bar for. I'll click off my DVR since that's what I'm drawing on my right. Click OK, and it's a little off the screen, so you can adjust the positioning of all the different color bars. So I'm going to go back down, and for my DVR right here, my lower left X, I'm going to change that to maybe, just for demonstration purposes, 0.5. It might take a little bit of tweaking to get it in the right position for where you want, but there's my color bar that's associated with my transfer function on my DVR over here on the left. Amit asks, can NetCDF files be loaded directly without BDC? No, they can't. They are too broad and nebulous. There's a lot of things that need to be specified in order for Vapor to understand the grid that they are operating on. So NetCDF needs to be converted. Things like WRF, MOM, POP, Ocean models, even Ramses, those are the things that have enough metadata inside the files themselves that we can directly import those. Question from Arash. Which data formats does Vapor support? Can it directly read the compatible data for Visit software? So Visit actually eclipses Vapor in its data import capabilities. Vapor doesn't import the same variety of data formats as Visit does. The kind of native formats that Vapor does support are under Data. you can find those under import data into current session. And there's WRF, Mom or Pop ocean models. There's the ROM's ocean model, CAM, GRIB, certain flavors of GRIB, Icon, Impasse, and Ramses. We also support conversion for raw binary data and netcdf data. But for those, you need to find the right incantation on the command line to generate VDC. That's it. Okay, well, if anyone has any more questions, feel free to fire away. I can maybe just play around with Vapor for a little bit in case any more questions show up. Maybe I'll just mess with my Katrina data set for a bit. Let's see. So my DVR, Q Vapor. Let's try Q Rain instead. Actually, Katrina is not as exciting as the tornado. I'm going to open the tornado again. So I'll do new session, load a data set in the current session. And then I'll go down to ORF, where my data is, orf4.vdf. And I think I want to do some volume renderings of that vorticity magnitude variable because I just found out about that. So I'm going to go to Edit, Python, defining a new variable. And I'll do X, Y, and Z vorticity, and then add vort. Vort equals sqrt x vort times x vort plus y vort times y vort plus z vort times z vort. And if anyone out there has any more questions, feel free to fire away. I'm just messing around right now. Successful test, apply. And then, let's see, go to my volume, mouse mode, it's the full thing. And then enable my vorticity. Let's see what we got here. Fit data, fit to view, histo. More questions. One from Samuel. Can you save the new variables that you manually create? Yes, that is done through the session file. So I just made a vorticity variable right here. I'm going to go to File, Save Session. Gosh, for some reason my Save Session window isn't showing up. That's weird. I wonder if it has to do with the monitors. Maybe I'll try closing everything else. Don't save. That's kind of strange. I guess I can only explain it for you right now then. So according to the correct behavior, when you hit File, Save Session, there should be a dialog that will let you save a session file. And that will contain all of your derived variables. And then once you want to reopen it, you can go to, I think I have a session I can demonstrate that with right now. I'm going to close Vapor. I'm going to open it again. So now we're in a blank default session. I'm going to open a session that I had saved previously. And I'll go to ORF. And I should have, I don't know if that's the one I want. I'll just do dvr.session. And so, let's see, do I have, so after you load your session, then you must load your data. So the VDC data is a separate entity from your session file. So now I have to go to Data, Load Dataset in the current session, and now I have to pick orf4.vdf. So here we are. We have our session, we have our data, and then I think, yes, I had two velocity variables that I had derived before, and there they are. So let's see if this behaves as expected. Yeah, there's one of my derived wind velocity variables from before. So I hope that answered your question, Sam. Diana asks, do we need to download another program to use this Python derived variable? No, this Python, these derived variable capabilities are packaged with Python. So it comes with the application. You don't have to install any third-party libraries or dependencies. Okay, so let's see if I can do my vorticity magnitude again. Vort. Xvort, Yvort, and Zvort will be my inputs, and Vort equals sqrt xvort times xvort plus Yvort times Yvort plus Zvort times Zvort. Test. Okay, apply. And I'm going to make a new volume renderer. You guys can see I have 1, 2, 3. I have a whole bunch of volume renderers that I was kind of experimenting with before. So by clicking on New, I generate a new instance of my volume renderer, and I can tamper with that without affecting my previous work. And that applies for all renderers. You can create new instances of every renderer and save different states if they show something that you like. So my new renderer, I'm going to pick on Vort, and it looks like I'm only rendering to this small rectangle, this little monolith. I'm going to go to my region and expand this back out to the full domain. And gosh, before I crank up the resolution, I'm going to do fit data, fit to view, histo. And this kind of demonstrates how you can explore the data at a low refinement level before you crank up the resolution and start taking a long time with your renderings. I'm going to load my favorite transfer function, this one here at the top. And then I'm going to draw the opacity down on those black values. And then one popular way to do a transfer function is to do a ramp like this, so that the values on the right side, which are very minuscule, there are very few values of vorticity at the right side, those are highlighted the most because my ramp is the highest up right here. It's very high up on the y-axis, and so the values that don't show up often are very prevalent, and the values over here on the left that are proliferous through the data set, those are kind of muted because my opacity ramp is very low over there. So let's see, I'm going to drag this over so that all the black and blue values are pretty much completely silenced, and we start showing our data at this very tail end of the histogram. I'll crank up my fidelity and see what happens. Yeah, it's really chugging. There we go. Maybe now I can try to associate some streamlines with what's going on here. I'll turn my fidelity a little bit lower. And let's just see what we got in this flow renderer. Okay, well, I mean, I guess that did the trick. We have streamlines now associated with that vortex, those streamlines coming in from the right. And then let's see what that renderer has. I think I had these streamlines coming in from the left to show what was going on either side of the tornado. Oh, no. Maybe not. Where are we drawing to here? Flow rake right there. So maybe I can bring it out. There we go. So here we have gold and silver streamlines coming in from two different regions, both getting sucked straight up into the tornado. I'm going to turn my vorticity off. And then, why not? I'm going to take Okay, instance 2 are the gold streamlines coming in from the left. I'm going to duplicate those. So I can make a copy of my renderers as well by clicking duplicate in this visualizer. I'm going to click on instance 3 right now, and I'm going to drag instance 3 over to the other side just to see what the flow is doing differently over here. Before I enable it, I'm going to go down and select a different constant color, maybe a red-ish color. Try that and enable it. And while the flow really does vary wildly depending on what side of the tornado you're on. And I can do the same thing for the opposite side of the silver flow lines, I guess. So the silver one is instance 1. I'll duplicate that instance in this visualizer. Go down to instance 4, drag it over to the other side. Maybe I'll do green on this one. And enable. Huh. So it doesn't look like much gets sucked into the tornado at all. Oh, another question. Okay. Samuel's asking about unsteady flow. Yes, if there's time. Yeah, I should do that. Okay, so for unsteady flow, I'm going to disable 1, 2, 3, my 4 flow renderers. And for my flow rake, unsteady flow is more computationally expensive than steady flow because it's loading every data set depending on how you specify the integration of flow. I'm not sure if that makes too much sense, but hopefully it will after I give a little demonstration. So I'm going to reduce the size of my flow rake right here. And I'm going to scroll down. Actually, okay, so I have, where is it? Right here under type. Right now we're doing steady flow. I'm going to click on unsteady flow. And that's going to bring up a whole different set of options because unsteady flow is a different animal. I'm going to bring this guy a little bit out further. And scroll down under show flow seeding settings. And let me get my RGB arrows on so I know what axis is what under edit visualizer features. And where are we? Show XYZ RGB arrows. Okay, so my X is red, my Y is green, my blue is Z. And I think I will do maybe 10 on the Y-axis, 10 seeds on the Y-axis, and maybe 10 seeds on the Z-axis, only 1 on the X. I'm at a decent fidelity so I don't bring my computer down to its knees. And then I'm going to show unsteady flow seeding settings. I'm sorry, the time settings is what I'm looking for. So this top panel here, or this top set of arguments, C times start, end, and increment, tells Vapor when we're injecting seeds and by what increment. So for example, right here, I will inject seeds starting at time step 0, ending at time step, let's see, how many do we have in this data set? We have a total of 5. Our index starts at 0. So our end increment will be at 4. So I'm going to inject a seed. If I have this last parameter as 1, that means I'm going to inject 1 set of seeds every time step from time step 0 to 4. If I change this from, I guess, 3 to 4, I would have seeds injected at time step 3 and time step 4. And if I had this go from 0 to 4, and I had my increment at 2, it would inject seeds every other time step. If I had it at 3, it would be every third time step. I'm just going to do 1. The time step sample start, end, and increment is the data points that Vapor uses to compute the flow integration. So the start and end times, I typically always have as matching to my seed time start and end. I think that's a good rule of thumb to go with. And so that means that Vapor will be sampling between time steps 0 and 4 to do your flow integration. If I had an increment of 5, that means that Vapor would only take 1 sample of wind speed because I have 5 time steps in my start and end period. So I think it's important for us to do 1 sample per time step. So we're sampling every single time step, and that'll be our flow, unsteady flow settings. So again, basically, I don't know if that made sense. It's a little bit confusing, but basically the seed time start and end and increment are when you're injecting, and the sample start, end, and increment are when vapor is reading the data. So that being said, I'll come up here. I'll enable that. Looks like we have an error message. And it's thinking. Oh, well, while that's working, the resolution of the data is 30 meters, and gosh, let me see what Lee's grid is real quick, because I don't remember off the top of my head, and I can find out what the grid is by looking at the VDF file. So vi orf4.vdf, and his grid dimension length is 485 by 501 by 280 grid cells. And the real-world resolution is a 30-meter resolution inside of the tornado. The supercell thunderstorm that he's simulating that spawns this tornado is, I think, 120 kilometers cubed, or at least squared. I'm not sure how high up it goes. But what we're looking at with the tornado is a subset of the supercell simulation that Lee created on Blue Waters. And gosh, another question. Okay, while Vapor's still running, I'll answer this. Can we add some timestamp information on the visualizer, like showing variable times of WRF out automatically on the plot? Yes, that is done. Gosh, I wish. Let me see if I can open up another instance of Vapor and show you that. Go to T, and this is how you guys will open up Vapor if you're using a Linux system. You'll just type Vapor GUI, and then you can also type in the data file you want to load on the command line. So I'm going to go to my file system. Ooh, it is slow. Ooh. Vapor data. Let me see. WRF. Katrina. Let's see if I can open up Katrina. Oh, wait, I'm not on the file system. Okay. Vapor GUI. Glade P-G. Vapor. Data. WRF. Katrina, and then I'll just open up katrina.vdf. So this will open up another instance of Vapor while that one's running. Or it should at least. There we go. Okay, so then to get that timestamp in, and my computer is kind of churning on that unsteady flow in the background. There should be a menu up here. Well, I guess while it's thinking, I can tell you that to get your timestamp information onto the plot, there's a setting in Edit under. If you click on Edit and then Edit Visualizer Features, there's going to be a whole bunch of things that you can add in, like those RGB arrows that we had earlier. There's going to be a drop-down selector for your timestamp annotation, and you can select like an actual timestamp, like a date and time, or you can select a timestamp number if you don't have date time information in your file, which I wish. I'm not sure why. Vapor's crawling right now. Maybe I did something bad earlier. Yeah, vapor's pretty locked up with this unsteady flow. Gosh, who asked the question about the unsteady flow? Samuel, I should at least point you to some documentation on it because we're running out of time. If you go to the Vapor website, documentation under Vapor GUI guide. Let's see, there should be data visualization. There should be thorough explanations of all the different renderers. In fact, I think you can just do search for flow, unsteady flow settings. And so there's documentation here on how to set all of that up. If you just do a Google search for flow on the main page. And if you're still having trouble, give us an email at vapor.ucar.edu and we can help you out and take a look at your data with you if it's, I don't know, if it's appearing funny. Well, we got about a minute and a half. I think Vapor is really thinking hard about this unsteady flow. I think it might be because the grid is so large. But I don't know. This is kind of strange. I think I might just wrap it up right now unless there's any more questions, guys. I'll wait one more minute, but there's really not much more I can do because Vapor is kind of locked up. Yeah, I think it's done. Oh, wait, here we go. So Vapor finally loaded with that new data set. And to show you where that timestamp annotation, we can click on Edit Visualizer Features, and then the time annotation is right here where it says no annotation. We can select timestamp number, and then I think since I have a white background, we should select black as the color. Click Apply. Okay, and there's time step 0 right there in the corner. I don't know if you can see that. You can bump up the size. I'm going to try 50. See how big we can go. Yeah, time step 0 right there. You just have to pick the color according to what your background is. I was white before, and so you couldn't see it like that. Okay, guys. Well, thanks for joining us. And again, if you guys have any questions, we're always available to help. So hopefully I'll get to meet some of you guys in the future. Thanks again. Bye-bye. Okay.